Hey steel friends, today I want to talk to you about bolted connections. So we've been through a bunch of different limit states for tension members. So we've been through yielding, fracture, and block shear. But we haven't really focused on the actual connection where the bolts are. So today's lesson is all about that. We got 5 big learning objectives to get through. So the first is to explain the difference between simple connections and eccentric connections. Then after that, we want to list and describe the different limit states that are applicable to bolted connections. Once we do that, we'll develop equations for the bearing strength and the tear-out strength. Then we'll look at calculating the shear strength of an individual bolt. And finally, we'll put all that together and solve some example problems. We're going to start with talking about the difference between a simple connection and an eccentric connection. So in a simple connection, basically as we apply the load, so I'm going to pull on this member in tension, as I apply that load, the center of gravity of the force is passing through the center of gravity of the connection. So I see that in this plate here, the center of gravity of the plate and the center of gravity of the bolt is in the same location, same line of action. So that is what we consider a simple connection. In a simple connection, we assume that every bolt handles an equal amount of load. So we already assumed this when we looked at our fracture and our block shear calculations, where we were adding up how much each bolt hole contributed to the total force. So basically, a simple connection, we assume that all the bolts share the load equally. Now, an eccentric connection doesn't have the same line of action of the force as the connectors. So take, for instance, if I flip this connection on its side and we look at this plate. If I was to load it vertically here and push down on it, the line of action of my load would be somewhere over here. But the center of gravity of my connectors, this weld here, is over in this plane. So I see that I have a force that is now eccentric at some eccentricity to my connectors. So that is what we consider an eccentric connection. Now, in our undergrad steel class, we're going to focus on simple connections. So we're going to focus on this first one here, where we assume all the bolts handle an equal amount of load. The problem with an eccentric connection is that some bolts handle more load or less load due to bending moment or prying action, and we need to account for that. So we're going to look at simple connections. Let's go ahead and take a look at some of the definitions. Okay, so in a simple connection, the line of action of the resultant force passes through the center of gravity of the connectors. So therefore, each connector is assumed to share an equal amount of load. So we did this when we looked at fracture. We said that each bolt hole was holding, a certain percentage of the load. So if we had 8 bolts, we said that each bolt was holding 1/8 of the total load on the connection. So that assumption is one of the assumptions we make when we assume we have a simple connection. In an eccentric connection, we don't have the line of action of the resultant force passing through the center of gravity of the connectors. Therefore, there is potential for stress gradient, moment, or prying action in the connection. So moment, bending, prying, all of these things will create increased forces on some bolts and decreased forces on the other. Or it could even create the condition where we have to have the bolts are holding a combination of shear and tension. We're going to focus on simple connections in our undergraduate steel course. Next, we'll draw a few schematics of simple connections versus eccentric connections. So we saw the real-world physical models already, but let's have a couple of schematics in our notes. So let's consider just a very simple lap splice connection with 2 plate members. So here I have the left member is on top of the right member, hence the dashed lines there, the hidden lines. And now we're going to pull on this with some sort of tension force. All right, and we have to draw in some bolt holes. So I'll go ahead and even make this a staggered bolted connection. Have a total of 8 bolt holes. So if we look at the bolt holes, this is the center of gravity of the bolt holes. So this is what we call the center of gravity of the connectors. So we see that the center of gravity of the connectors and the location of the force, the line of action of the force, the tension force, passes through that center of gravity of the connectors. We don't have to restrict this to just talk about bolts. We can also look at welds. So let's consider this lap splice where the left member is welded to the right member and we're pulling on in tension. I'll denote that welding with a little bit of a green scribble here. So we see that if we were to take the center of gravity of that green scribble, we would also find the center of gravity would be somewhere around there. That matches up to the same line of action of our force. Now in an eccentric connection, this is not the case. The line of action of the force is not in line with the center of gravity of the connectors. So one of the classic examples of an eccentric connection is if we consider sort of a plate that's been welded to a column. I'll go ahead and draw a plate that's now attached to a column. And this plate is going to have some sort of vertical force on it. And the plate could either be bolted to the column, it could be welded to the column, however you want to assume it's connected. It's somehow connected there to the column. In any case, if we consider like the bolted connection, this is the center of gravity of the connectors. And if we are applying a vertical force on this plate, and we apply this vertical force out at the tip of the plate, we see that the vertical force, the line of action of that force, does not pass through the center of gravity of the connectors, whether it be the center of gravity for the bolted or the welded connectors. This line of action does not pass through that center of gravity. Therefore, that makes this an eccentric connection. So as this plate would be pulling down and bending, the top bolt would also have some sort of horizontal force applied to the right. The bottom bolt would have some extra compression there as the plate is rotating. And so we'd have to account for that in our design. Finally, I've been using the term connectors. What do we mean by a connector? We mean any kind of structural fastener. So mainly right now you should be thinking either bolts or welds. And these will be the most common types of fasteners that we are interested in learning about right now. In new construction, this is what we're going to use. For bolts, bolts have a couple of different groups. We have groups A, B, and C, as well as other grades of bolts that we can use. We also have different strength welds. However, in the past, we have some other fasteners that we've used. So I'd say these are more historical fasteners. We've used in the past pins, rods, and eye bars. And then we've also used rivets. With rivets, you basically take it looks like a bolt, except it's a smooth cylindrical shape. And you heat it up to red hot, and then you pound it through the hole. And as you do that, you kind of mash the metal around, and then as the metal cools, it draws the two pieces together. So rivets were used on many structures, especially in the early 1900s. We'll take a look at one in San Angelo. Hey there. We talked about, in this class, we're only going to focus on bolted connections, because bolted connections are pretty much what we're going to design nowadays. But when are you going to ever will you need to know about riveted connections? Maybe. Right? So you can see if you have a historic structure, such as the Lone Wolf Bridge here in San Angelo, you're going to see examples of rivets. So maybe if some problem existed on this bridge and your firm was asked to come in and evaluate the structural integrity, you might have to do a little bit more research about rivets. But pretty much, by and large, most of your design is going to be with steel bolted connections. So that's what we're going to stay focused on. I want to get back to our simple bolted connection that we have here. Now, there's two possibilities when we're looking at the bolt limit states. First, we want to design the bolt connection for bearing. What that means is that these two plates, right, these two plates can't separate because I physically can't pull them apart. So this is bearing, or this plate here is bearing upon the bolt, which is then bearing upon this other plate and transferring the load. Now, we will eventually also talk about slip critical connections. In a slip critical connection, I will be able to tighten this bolt down strong enough that now the two connections will not slide. So I'm basically using like the friction force developed by tensioning this bolt to prevent slip. So that's going to be a slip critical connection. We should always design all connections to meet bearing strength conditions. So let's focus on the first bearing strength limit states. And then for this bolted connection, I want you to think about what are some of the ways in which this bolted connection will fail. What could happen? So kind of think about that as I'm trying to pull these two plates apart. How would it possibly fail? So I hope you're able to come up with a few ideas that you might have had. One is that the bolt will simply shear apart, right? So that's what we consider bolt shear. So as we pull on that, the bolt would physically separate across itself, and that's going to be in shear. So we're going to have to definitely get bolt shear. But what are some of the other things we can do? What if the bolt is super strong relative to the plates? So to help us with that, I want to visualize what that would look like. And so I'm just going to grab a piece of paper. So you can do this little experiment in your house. And you can check this out. We're going to have the bolt. The bolt is much stronger than the material that it's attaching. And we stick the bolt into the bolt hole, and we see it fits nicely. And now I will pull on it, and I'm going to pull in this direction. So let's watch. What do you think is going to happen? Hopefully you guessed it was going to rip out. This is what we call a tear-out failure. So as we pull on this, the bolt tears out the end. And we see that we get sort of this kind of bent, deformed, some sort of failure surface there. In addition to tear out, we could also be concerned that it moves, but it doesn't quite rip entirely. So in all directions, it could move a little bit and bear against the plate. So we call that a bearing failure. So basically it just looks like the elongation of the hole. So you'll see that the hole was deformed, but we didn't actually fail it. So those are kind of properties of the material that we're attaching. So we need to check the bearing strength, and we need to check the shear tear-out strength. All right, recapping our failure modes for bolted connections, we need to have all the member connection plate failure modes. So that's going to include yielding, fracture, and block shear that we already have learned about for tension members. It's also going to include the tear-out failure and the bearing failure at the bolt holes. So those affect the strength of the base member or the connection plate. In terms of the bolt, we talked about having just the shear failure of the bolt. So the bolt physically separating from itself. We also have other possibilities, bearing failure of the bolt, which isn't typically the case since the bolt's usually a higher strength than the plate. So we usually don't have to worry about that. Bending of the bolt. We have tensile failure of the bolt, so we'll see that indirectly when we look at shear failure of the bolt. We'll also kind of come up with the tensile failure of the bolt strength. And then finally, we have to look at slip of the connection. Lastly, we didn't take into consideration the actual construction of the connection yet. So there's going to be two constructibility concerns, the minimum spacing and edge distance requirements, as well as maximum spacing and edge distance requirements. Next, I just want to point out this table J3.3. This has different bolt hole types. So we've looked at standard bolts, which is very typical. This is what we use for most construction. However, there are sizes for oversized, short slot, and long slots. You can reference this table for all the sizes, including the standard size bolts, and that's what we need to use in all our calculations. A little bit more on constructibility. We have different hole sizes. So we have mainly focused our attention on standard hole sizes. So for a 3/4 inch diameter bolt, the standard size would be 13/16. So that is what this hole is, and this is a 3/4 inch bolt. So we see that as we insert the bolt, we have a little bit of wiggle room. We need that because we need to have a little bit of flexibility, because as you have a very large connection, multiple bolts, you have to have the ability to move your member and pry your member around a little bit to get those bolts through. So that's what a standard hole looks like. We also have an oversized hole. Now for an oversized hole for a 3/4 inch bolt would be closer to 15/16 inch. Is what the specification tells us. So this 13/16 inch is actually oversized for a 5/8 inch diameter bolt. So I'll go ahead and put a 5/8 inch diameter bolt in here. And you'll see that this is what an oversized connection looks like. An oversized connection gives us a lot of wiggle room. We don't really like to use oversized connections if we don't have to. We typically will always use the standard size connection unless you have some sort of geometry that's going to require you to have a little bit of extra play in your connection. Finally, the other two types of bolt holes are slotted holes. So slotted holes come into play, especially like maybe in like a bracing member where you want to have some ability to move back and forth. And so slotted holes look something like this. Now for structural connections, we're only allowed to build the structural connections so that the slotted holes are loaded perpendicular to the bolt so that we don't have a lot of that play in there, right? We don't want to load it along the length and have the potential for the bolt to slide. So we don't want to do that. So this gives us the ability to have our structural bolt and be able to adjust our member side to side. But then we would have to make sure that we're loading perpendicular to the slot, both for long slotted holes and short slotted holes. A lot of times with slotted holes, that's where we're going to use what we call a slip critical connection, where we want to tension that bolt and prevent that slide using the tension force from the bolt to create friction between the two connecting elements.